The universe, uh, it kind of hides its greatest secrets in plain sight, doesn't it? Often revealing them not through, giant telescopes pointed way out there.
Right, but sometimes through equations so simple you could almost scribble them on a napkin.
Exactly. And we're talking about this surprising link, this connection between, say, the massive spiral arms of a galaxy and these tiny, endlessly repeating patterns you find,
Yeah.
well, everywhere in nature.
It's that feeling of wonder, isn't it, when you see lightning fork or maybe the way a river delta branches out or even just the pattern on a fern leaf.
Yeah.
That feeling, it hints at something deeper, some kind of underlying mathematical law maybe, and people have been chasing these patterns for, well, millennia,
Right.
trying to find the source of all this order.
So today, we are really diving deep into a body of work that takes one of the most, I think, remarkable discoveries in modern math, the Mandelbrot set,
Oh, absolutely.
and uses its ideas, infinite complexity, this perfect mathematical order, to tackle some really big philosophical questions, questions about whether knowledge is constant, about creation itself, and even arguments for divine intelligence.
Yeah, our mission here is really to look closely at sources that treat this discovery, which, let's face it, only happened because of computers, not just as a cool math thing, but as, well, profound evidence. Evidence for a fixed, constant governing order in the universe.
It's fascinating how a purely abstract calculation can become, for some, a cornerstone for a whole theological argument about how reality is put together. So this deep dive, it's designed to give you a pretty quick but hopefully thorough understanding of how really simple math rules can generate this conceptual infinity, and how some viewpoints interpret that as solid proof of a higher, unchanging structure underneath everything.
We've got some heavy hitters today. Deep math, philosophy, a bit of history, theology, all sort of converging on this one, honestly, beautiful shape.
Okay, let's get into it. Let's unpack this.
Right. So the Mandelbrot set. To really get why it's so significant, we probably need to start with its discovery, or maybe its visualization.
Okay, because the math itself, the pattern it describes, that's always existed, right? Like theoretically.
Exactly. Conceptually, it's been there since the beginning of time. A constant mathematical possibility. But actually seeing it, discovering it visually, that's incredibly recent. We're talking the 1970s. Benoit Mandelbrot, the mathematician it's named after, was key.
And the crucial piece of the puzzle, the thing that made it possible to actually see this thing, was the computer. The digital computer.
Absolutely essential. Before we had computers that could crunch numbers like that, trying to generate this pattern. I mean, imagine thousands of mathematicians working for centuries.
We couldn't do it. Not with pencil and paper or even a slide rule.
No way. It was the ability of those early computers to just churn through billions of calculations, these repetitive, iterative calculations, really fast. That's what finally let us, see this structure that was hiding in the numbers all along.
And what's so wild is that the equation itself, the core rule, it looks almost simple, deceptively simple. Anyway.
It really is. But it produces this incredible, seemingly infinite depth. So the Mandelbrot set, it's defined by what's called an iterative equation.
Okay, iterative meaning you repeat something over and over.
Yeah, exactly. You take the result of one step, feed it back into the beginning of the next step, and just keep going. Like a chain reaction, or maybe compound interest is a good analogy. You keep applying the same rule to the previous outcome.
Got it. Okay, so let's look at the actual formula. It's ZON plus 1 plus 1 plus C at T. Looks a bit scary, maybe.
It can look intimidating, yeah, but the process is actually pretty straightforward once you break it down.
So what are the pieces? Z and C.
Right. First, you need a starting point. For the Mandelbrot set, $0, the initial Z is always 0. That's our anchor.
Always 0. That's
Complexity, the whole shape, everything comes from that other value, $.
And $. Is different for every point you test.
Yes. $. is a constant for any single point you're checking on the screen on the graph. And here's where it gets interesting. $. is defined using complex numbers. So $2 are X plus IYR.
Ah, complex numbers. Okay, quick refresher for maybe some of us.
Oh, that's
$CLs are just coordinates, right? Like how far across and how far up on the graph.
Exactly. $6 is the horizontal position. Dollars is the vertical position of the specific spot on the plane, whose fate, whose color. We're trying to figure out where are we on the map.
But the I, that's the kicker, isn't it? The imaginary number.
That's the revolutionary part, yeah. IL is defined as the square root of -1. Which sounds weird because, no real number multiplied by itself gives you a negative.
Right. A minus times a minus is a plus, and a plus times a plus is a plus.
So $y is called imaginary, but when you combine a real number part $0.06 with an imaginary number part, you get what's called a complex number.
And visually, on this graph, the complex plane, the real part is horizontal. Imaginary is vertical.
Correct. That eye is what gives the whole thing its two-dimensional structure and allows for the twisting, the rotation, the spirals. If it was just real number, you just get points on a line. Multiplying by liars is like rotating 90 degrees on that complex plane. That rotation is absolutely key to the beautiful, complex shape we see.
Wow, okay, so for every single pixel on my computer screen, I figure out it's 6 in dollars, make that my x plus iy. Then I start with z dollars and run the formula. Z dollars will be 2 plus c, then z dollars will z12 plus c, then c dollars is z22 plus c dollars over and over.
That's precisely the iteration process. You plug the previous result back into the equation, square it, add the original c for that pixel, and get the next result, z and m plus 1.
Okay, but how long do you keep doing that? When does it stop?
Good question. The computer keeps running that calculation until one specific condition is met. Basically, when the resulting number, z(n)(mallar, gets too big. Mathematically, we check if its magnitude, its distance from 0 on the complex plane, exceeds 2.
Greater than 2. Why 2?
Yeah.
Is that arbitrary?
It's not arbitrary, actually. It's mathematically proven that if the magnitude of z ever exceeds 2 at any step, it's guaranteed to shoot off towards infinity if you keep iterating. It's like it crossed a point of no return. It escapes.
Ah, okay. So if it escapes, say really quickly, maybe in just 5 steps.
Then the computer assigns that starting point, that pixel, a specific color, maybe blue.
And if it takes like 1,000 steps before it finally gets bigger than 2 and escapes?
It gets a different color, maybe yellow or red. The color often represents how many iterations it took to escape. That's what creates those beautiful swirling colored bands you see around the edges of the main shape. It's like a map of escape velocities.
Okay, that makes sense. But what about the points inside the main shape?
Yeah.
The black bits.
Right. Now here's the magic. If the number, after maybe hundreds, thousands, maybe even millions of iterations, if it never gets bigger than 2, if it stays trapped, contained, bounded within that circle of radius 2, then that starting point, that $2 value, belongs to the Mandelbrot set itself. And traditionally, those points are all colored black.
So the black shape is the collection of all the starting points that don't escape to infinity when you run this iterative process.
Exactly. Those are the points that defy the pull towards infinity. They form the iconic main ship. It looks a bit like a cardioid, a heart shape, and all the little bulbs and filaments attached to it.
And when you zoom in, particularly near the edge of that black area,
that's where it gets really mind-blowing. You zoom in on the boundary, those intricate edges between the black set and the colorful escaping points, and you start to see, well, miniature copies of the entire Mandelbrot structure repeating.
Little baby Mandelbrots tucked away in the fuzziness.
Yes, and the detail, the complexity, the repetition just keeps going. You can zoom in indefinitely, and you'll keep finding more structure, more self-similar patterns. It continues without an end in sight. That self-similarity across all scales is the hallmark of a fractal.
Which leads us to this really bold claim in the source material, that this is infinity proven by science. That feels huge. Is that fair to say? Isn't infinity more of a mathematical concept, not something you prove like gravity?
That's a really sharp question, and you're right to pause there. From a purely rigorous mathematical standpoint, what the Mandelbrot set demonstrates is a conceptual definition of infinity. It shows that a fixed, simple set of rules can generate complexity and detail that have no theoretical limit.
So it's infinite in potential detail because the process never has to stop.
Exactly. Because the rule, z2 plus c2, is fixed, and the iteration can conceptually go on forever without the pattern repeating exactly but always showing similar structures, the output complexity is guaranteed to be non-terminating. The sources we're looking at are interpreting this conceptual mathematical proof as a kind of empirical demonstration of something truly endless, eternal.
I see. So they're using this visual computational result to bridge that gap between abstract math and something more tangible, almost physical feeling, even though it's on a screen.
Precisely. And you can't just look at the coordinates, the 7 value, and know if it's in the set or not. You have to run the calculation maybe thousands of times. It's a completely deterministic process. The outcome is fixed by the rules, but the result? It strikes us as having immense aesthetic beauty.
Yeah, it really does.
And the fact that these simple, predictable rules, including how imaginary numbers work, like 1 times I wills night to 1, 1, the fact that these can yield such apparently limitless complexity, that's the core insight the sources are running with.
It shows that you don't necessarily need incredibly complex rules to get incredibly complex results.
Exactly. A simple fixed algorithm is enough to generate what looks like an endless universe of detail. Detail that never quite repeats but always looks familiar. And this deep structure, generated by pure math, is what our sources start to identify as a kind of underlying harmony or order in the cosmos.
Okay, so that harmony, that structure, leads us straight into the bigger picture of fractal geometry, which is sometimes called a universal pattern language, right? It describes shapes and forms that old school Euclidean geometry, perfect lines, squares, circles, just couldn't really handle.
That's a great way to put it. Traditional geometry works well for smooth, regular shapes. A fractal, though. Well, the definition is something like a non-regular geometric shape that has the same degree of non-regularity on all scales.
Meaning it looks similarly jagged or complex no matter how much you zoom in or out.
Essentially, yes. It's about never-ending patterns where, statistically at least, the part resembles a whole. And this type of geometry has become absolutely fundamental now for understanding complexity, for modeling chaotic systems, even for describing the messy bits of the physical world.
And the Mandelbrot set is kind of the poster child for fractals. But the sources we're looking at, they emphasize that this type of pattern, this fractal structure, isn't just a mathematical curiosity. They argue it's everywhere.
Ubiquitous, yeah. Found in seemingly every living thing. They point to the branching structure of our lungs or blood vessels.
Or trees, or how cells divide.
Right. It's presented as the place where abstract numbers and tangible nature really collide.
And that collision point, that's where the interpretation gets really deep in these sources. They see this mathematical blueprint underlying so much physical structure as, well, they use the phrase God's signature.
An unmistakable sign of deliberate, intricate, intelligent design woven into the fabric of reality.
And to bolster this theological argument, they bring in references from the Quran, specifically verses where the Creator seems to be inviting people, urging them to look closely at the power, the precision, the sheer beauty of the natural world as evidence for the truth of the message.
Exactly. The examples they cite are all about establishing the observable universe as a place of deliberate, consistent, flawless order. It's not random chaos.
So what are some examples they use?
Well, first they look upwards, cosmically, thinking about the heavens, the sky, which visually, with its spirals and nebulae, can sometimes echo the Mandelbrot set. They quote from the Quran, chapter 50, verse 6, which asks, rhetorically, "Have they not then looked at the sky above them, how we built it and adorned it with stars, leaving it flawless?"
Flawless, that's a key word there. The assumption is perfect, underlying order.
Yes. Then they point to the mechanics, the predictable movements in the heavens. Chapter 21, verse 33 says, "It is he who created the night and the day, the sun and the moon, each of them is floating in its orbit." Highlighting a system governed by constant, predictable laws. A system that, obeys the math.
It follows the rules.
It follows the rules. And then there's a kind of summary statement of this perfection in chapter 67, verse 3, asserting, "You will not see any imperfection in the creation of the most gracious. So turn your vision again. Do you see any flaw?" It's this repeated emphasis on the consistency, the predictability, the perfection of the observed universe. And that's presented as theological evidence that mirrors the predictable, perfect generation of the fractal formula.
This brings us to a really crucial distinction that fractal geometry kind of forces us to make, and one that the source material really leans into heavily. It's the difference between the purely conceptual world and the physical world we actually live in.
Right. This is key. In pure mathematics, we can talk about perfect fractals, like the Mandelbrot set rendered perfectly by a computer. These repeat infinitely, precisely, following the rule absolutely at every conceivable scale. You can mathematically zoom in forever.
But these exist only in the realm of concepts, in the world of pure mathematics.
Exactly. They are ideal forms, abstract perfection.
But the world around us, the physical world,
Yeah.
that's different.
Yes. The physical world contains what scientists often call proximate fractals or approximate fractals.
Okay, like what?
Well, think of a coastline on a map. It looks jagged and complex from far away, right?
Yeah.
Zoom in with a helicopter, it still looks jagged and complex, just revealing more bays and inlets. Similar kind of complexity. But if you zoom in far enough, eventually you get down to individual grains of sand, then molecules, then atoms.
And at that point, this self-similarity breaks down. A grain of sand doesn't look like the whole coastline.
Precisely. It's an approximation of a fractal, not a perfect one. A tree branches in a fractal-like way, but eventually you get to the cells, and the cell structure doesn't look like the whole tree. Physical fractals have limits.
So the source material draws a really sharp line here. The perfect infinite mathematical rule exists conceptually, perhaps eternally, but its physical manifestations in our universe are just variations, approximations, echoes.
That's the idea they put forward. And they drive this point home by specifically mentioning that something like uniform atoms are not fractal. They have a definite scale and structure. This reinforces the gap they see between the perfect, abstract mathematical concept and its sometimes messy, always finite approximations in physical reality.
And this whole philosophical view that reality is governed by these ideal, perfect mathematical laws that only show up imperfectly in the physical stuff that's had a big impact, hasn't it?
Yeah.
Even on culture and art.
Oh, absolutely. You can see echoes of this thinking reflected in various cultural expressions.
Like in Islamic art. The source brings that up specifically.
Yes, it points out that traditional Islamic art, especially the geometric patterns you see in mosques and tile work, often involves hierarchy, symmetry, repetition, creating these incredibly complex tessellations.
And they do often look visually similar to the kind of complexity you see in fractals, like the Mandelbrot set. Lots of repeating motifs at different scales.
Exactly, and the source suggests this isn't just a coincidence, it stems from a deeper philosophical or theological drive.
Rooted in the concept of Tawhid, the oneness of God.
Right. The tradition in Islamic geometry often avoids depicting human or animal forms, focusing instead on these complex, repeating, non-representational designs. It's understood as a way to represent the infinite, unified nature of the Creator through endless patterns and perfect symmetry, using abstract geometry to point towards the divine without creating idols.
So that aesthetic preference, that artistic impulse, it aligns really well with the kind of beauty we find in something like the Mandelbrot. Set infinite complexity from simple rules, endless repetition with variation.
It does, and in that context, exploring mathematical beauty, understanding these patterns, isn't just some dry intellectual thing. It becomes an act of appreciating creation, maybe even an act of worship. And they connect this to a prophetic saying quoted in the source, Allah is beautiful and he loves beauty.
Implying that the very structure of the universe is inherently beautiful because it reflects the attributes of its creator.
That's the connection being made. The Mandelbrot set, in this view, becomes this kind of modern visual bridge. It demonstrates that these deep principles, infinity, complexity from simplicity, repetition, underlying order principles that artists and theologians have contemplated for centuries, are actually quantifiable, mathematically generated by an incredibly simple, constant source code, if you will.
Okay, so we've got this simple equation generating infinite complexity. And we see echoes of that complexity in the natural world, in fractals. Now, the conversation shifts gears a bit, moving from the pattern itself to the fundamental nature of mathematics and numbers, because this is where the source material makes some really bold and, frankly, contentious philosophical arguments.
Yes, the core issue becomes the abstract, unchanging nature of mathematics itself.
Right. Let's really try to nail down this abstract nature first. Math is conceptual, it's not physical. That seems crucial to their point.
It is absolutely crucial. You can't physically touch the number 5. You can hold 5 apples, but the concept of fiveness itself isn't a physical thing.
A number itself has no physical power. It can't push you or hurt you. Only a physical object, influenced perhaps by mathematical laws, can do that.
Exactly. And even the symbols we use, like the numeral 7 written down, that's just a representation, right? A symbol humans invented to stand for the abstract idea of 7.
So the argument is that the laws of mathematics, the relationships between numbers, they operate independently of us, whether or not humans are around to write them down or think about them.
That's the stance taken, which immediately brings up that classic question. Is mathematics something we invent? Like a game with rules we made up? Or is it something we discover, like finding a continent that was already there?
And the source material comes down firmly on the side of discovery.
Very firmly. It argues that math is a pre-existing reality. Its laws are woven into the fabric of existence.
Okay. And taking that stance that mathematical laws are constant, universal, discovered, pre-existing, that leads directly to a really significant challenge to source material levels against.
Well, against the theory of evolution. Yes. This is probably the most provocative claim. The source argues that the very constancy and permanence of these discovered mathematical laws automatically disprove the theory of evolution, or at least disprove the idea of gradual fundamental change across all aspects of reality.
Whoa. Okay, that's a massive claim. We need to unpack the logic there very carefully. How does the fact that $1 plus EVA1 always equals $2.2 somehow refute gradual biological change over millions of years.
The line of argument goes something like this. If the physical universe were truly in a state of constant, undirected, gradual flux, if everything, from the simplest particles to the most complex structures, was slowly evolving and changing its fundamental nature over vast eons, then the foundational rules of that reality, including the mathematical laws that describe its behavior, should also be evolving. The source kind of rhetorically posits this idea of evolved mathematics.
So the thinking is, if physical laws like gravity might theoretically subtly change over billions of years as the universe expands and cools, then mathematical relationships, like the value of pi or the properties of prime numbers, should also have undergone some kind of slow, gradual evolution.
That's the parallel they draw. They argue it's inconsistent to say physical reality is fundamentally fluid and changing, but the abstract rules it follows are perfectly rigid and eternal. They'd say, you can't logically suggest that the concept we call 11 might have actually been the concept 3 billions of years ago, and it just evolved.
Or that the rules of how imaginary numbers work might have been different in the early universe.
Exactly. The laws of mathematics appear non-negotiable, internally consistent, and unchanging across all of known time and space. We rely on that very constancy to do all our science, calculating everything from the Big Bang back to predicting future planetary orbits.
So because math is constant, the source asserts, this stability fundamentally contradicts the idea of a reality based on universal, gradual, evolutionary change.
That's the core of their assertion. It challenges the universality of the evolutionary principle, suggesting it can't apply to these fundamental, abstract laws.
But couldn't someone push back on that? Couldn't you argue that math is constant because its rules are based on definitions that we hold constant? We define what 1 means, what plus means, what lamb means. Their consistent relationship follows from those definitions. It's a closed logical system. Is that different from discovering an external pre-existing truth?
That's a very fair counterargument, focusing on the difference between analytic truth, true by definition, and synthetic truth, true about the world. The source material seems to anticipate this. They might concede that humans invent the symbols, the numerals, the notation.
Like 2 versus 2.
Right.
Yeah.
But they would argue that the underlying relationships and laws, things like the commutative property a plus b equals a, or the fundamental theorem of arithmetic, these aren't just arbitrary definitions we made up. They are inherent properties of quantity and structure that we discovered. Their constancy is the key point. They exist and hold true whether we observe them or not.
So the Mandelbrot set, for example, all its infinite detail and properties existed as a mathematical potential inherent in the z-doll plus c-doll rule long before Mandelbrot or computers came along. It was just waiting to be found.
That's precisely the view. It wasn't invented, it was discovered. Its rules are fixed and eternal. And the source argues if reality at its deepest level were truly fluid and evolving, why would these fixed, eternal, abstract rules describe the physical universe so perfectly?
Which brings us back to that bigger, perhaps even deeper, philosophical puzzle. The one the physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences.
Exactly. Why does math work so well? Why does this abstract, conceptual thing we do in our heads provide such a powerful and precise language for describing the physical world, the universe? Why does the universe seem to obey mathematical laws?
From the perspective of someone holding a purely materialist or secular worldview, the source characterizes this incredible correspondence as, well, a perplexing dilemma.
Yes. How does mindless matter and energy somehow organize itself according to elegant, complex, timeless mathematical principles? The consistency between external reality and our internal abstract logic. It can seem almost miraculous if you don't assume a deeper connection.
It really is astonishing when you stop and think about it.
Yeah.
We come up with these purely conceptual laws in our minds, like EVMC 2 pillars or the rules for quantum mechanics or even the iterative steps for the Mandelbrot set, and they turn out to perfectly predict or describe the behavior of actual physical things, from tiny particles to whole galaxies.
The source puts it starkly. The very fact that laws of nature exist and that they correspond perfectly to the capacity of the human mind to discover and understand them, that in itself is presented as a kind of miracle. It implies some sort of pre-established harmony, right, between the observer and the observed, between the abstract rule and the physical result it governs.
And this is where they make the next leap. If mathematical laws are abstract, conceptual,
then they must have an abstract conceptual source. The argument made in the source material is that concepts like justice, beauty, or even the concept of the number 2, they require thought. They require reflection. They require a mind.
Okay, I see where this is going. if mathematical laws are conceptual.
And if they are constant and predate humanity, as argued.
Then the logical conclusion, according to the source, is that a mind with a capital M presumably must have existed before human minds did, to conceive and establish and perhaps sustain those timeless laws.
That's the core implication they draw. It's a profound one. The secular worldview, they argue, struggles to provide a meaningful account for why numbers and mathematical laws have the properties they do, if everything ultimately arose from random, mindless processes.
Why would reality be governed by these elegant, abstract, perfect, and constant conceptual rules? Especially rules that apparently existed long before any human brain evolved that could possibly comprehend them.
Exactly. So the Mandelbrot set, in this particular analysis, kind of acts like a digital smoking gun. It's this purely deterministic, predictable output generated by a simple, fixed, abstract rule, yet it displays infinite, non-random, structured complexity.
So if the starting rule is constant and perfect, and the output it generates is infinitely ordered, the source argues this points strongly toward an incredibly ordered, non-evolving intelligent source at the very foundation of reality itself.
And that line of reasoning, arguing from the constancy and intelligence inherent in mathematics to a pre-existing mind, transitions us very naturally into the specifically theological worldview presented in the source material.
Right, where this mathematical perfection and constancy find a perfect home, conceptually speaking, it aligns directly with the attributes ascribed to the Creator in this view.
Exactly. For believers, the source suggests, discovering this kind of perfect, constant underlying structure isn't just intellectually interesting. It offers deep reassurance. It connects to that idea of finding peace through connection with the divine order. They reference the Quran, chapter 13, verse 28. Verily, in the remembrance of Allah do hearts find peace.
So the mathematical order, revealed by something like the Mandelbrot set, becomes a kind of modern remembrance, a reminder of the Creator's constancy, consistency, and maybe wisdom.
That's the interpretation. And the consistency is really emphasized. The Quran, they point out, is itself consistent in its call for people to reflect, to really look at the world's beauty, its intricate detail, its underlying order, and see that as evidence.
So the mathematical certainty found in exploring fractals is presented as a kind of modern confirmation of this ancient invitation to reflect on creation.
Precisely. And the divine role in this picture isn't just about starting things off. It's described as constant guardianship, a continuous function needed to maintain that order to ensure the laws remain constant. They cite chapter 39, verse 62. He is the creator of everything. He is the guardian over everything.
So not a clockmaker God who wound up the universe and walked away?
No, definitely not in this view. It's more like a continuous, active upholding of the very laws, the mathematical and physical rules that define existence moment by moment.
And this guardianship, this creation, it extends even to the most abstract things, like numbers themselves.
Yes. The source explicitly states that the Creator is the creator of everything, and they include the numbers in that everything. The idea is that all things, tangible and intangible, function under divine intelligence and operate only by divine permission.
So the intelligence we perceive in the mathematical structure, like the predictable yet infinitely complex nature of the Mandelbrot set, that's seen as just a tiny glimpse, maybe a fractal reflection of the infinite intelligence of the one who established those rules in the first place.
That's exactly the idea, a small window onto an infinite reality.
And this order, this following of rules, it extends across all of creation. The source mentions the concept of submission or obedience to these laws.
Yes, drawing on chapter 22, verse 18, which asks rhetorically if you don't realize that everything in the heavens and earth submits to God, and it lists the sun, the moon, stars, mountains, trees, animals.
Basically, everything follows its nature, follows the laws set out for it.
Right. The perfect, almost mathematical obedience shown by the consistent behavior of natural phenomena, from orbits to biological processes, is seen as inherent in the structure of reality. Everything follows its unchanging, pre-programmed rule, much like a point iterating within the Mandelbrot set follows its determined path.
And seeing this universal submission, this perfect order, it underscores why knowledge is considered so important within this worldview. It's not seen as separate from faith, but maybe a path towards it.
Absolutely. Knowledge and reflection are presented as fundamental pathways to appreciating the Creator.
And this is powerfully symbolized, historically, by the very first word revealed in the Quranic revelation being ikra, which means read or recite.
Yes, that emphasis on reading, learning, seeking knowledge is foundational. The source contends that the more you learn, the more you uncover the underlying perfection and intricate complexity of existence.
The more your faith and your admiration for the Creator should naturally increase.
That's the argument. Seeing the beauty of the infinite complexity that can be packed into just a simple mathematical equation like Zn plus 1 plus 1 plus a CR, that's viewed as just a minuscule representation of the Creator's truly infinite power and knowledge.
And the nature of the divine itself is described using terms that echo this constancy we've been discussing. Attributes like omnipresence, omniscience.
And being ever-living, existing outside the constraints of time, which fits with the idea of eternal, unchanging mathematical laws.
Time itself is considered a creation, something with a beginning and an end.
Yes, time is seen as part of the created order, not eternal in itself. And its importance is highlighted. The source notes, by an oath taken upon time in the Quran, in chapter 103, swearing by time that humanity is generally in a state of loss, except for those who adhere to consistent principles of faith and good deeds.
So another parallel. Just as time provides a consistent framework for human moral action, mathematical laws provide the consistent framework for physical reality.
That seems to be the connection, yes. And finally, the source brings it back to the idea that all these patterns, these orders, these consistent rules, they aren't just there. They are meant to be signs for those who think, for the wise, for people who reflect deeply.
They reference chapter 30, verse 22, pointing to the creation of the heavens and earth, the diversity of languages and colors, all as signs for those with knowledge. So both the underlying unity, the rules, and the surface diversity, the outcomes, the proximate fractals, are signals.
Both are presented as signs pointing towards the same source. And even the most fundamental constant rhythm of our daily existence, the alternation of day and night, is highlighted in chapter 24, verse 44, as a profound, ongoing lesson for people of insight.
So the overarching message seems to be, nothing is accidental. Look closely, reflect deeply, and you'll see the evidence of perfect, consistent, intelligent order everywhere, from the grandest cosmic scales right down to the iteration of a single complex number in a fractal equation.
That captures the essence of the argument presented in the sources, yes. Hashtag tag OTRO.
Wow, okay, so where does this leave us? What does this all mean at the end of the day? We started this deep dive with what looks like a really simple mathematical formula, Z1 plus 1 and 2 plus C other 2.
Right, and we saw how with the help of computers it unveils this concept of scientific infinity, or maybe better, conceptual infinity, a pattern of literally endless complexity and detail, all generated by fixed, simple, deterministic rules.
And then we tracked how that intricate, unchanging mathematical order gets connected in the sources we examined to these really profound philosophical arguments. Arguments asserting that the very existence of eternal, abstract, perfect mathematical laws points towards an unchanging, intelligent source, a mind that must logically exist before the physical universe itself.
Yeah, in essence, the whole phenomenon of fractals, with the Mandelbrot set as a prime example, is used here as a kind of powerful modern metaphor. A metaphor for a highly detailed, intelligently structured, and fundamentally unchanging universal order.
An order where complexity doesn't just dissolve into randomness, but always adheres back to those initial, simple, constant rules, like points staying within the bounds of the set.
And this deep connection being drawn, it really challenges you, the listener, to think about how we reconcile these two worlds. The perfect, timeless world of conceptual, fixed mathematical laws and our actual physical reality, which seems messy, dynamic, always changing.
We explored that claim from the sources that perfect mathematical laws, perfect fractals, exist only in the conceptual realm, while the physical world only ever contains approximations, these proximate fractals.
So here's a final thought maybe to leave you as something to mull over. If the fundamental rules of the universe, the deep mathematical laws, are truly abstract, perfectly constant, and eternal.
But they only ever manifest in the physical world as variations, as imperfect approximations like trees that aren't perfectly fractal down to the atom, or coastlines that smooth out at the smallest scales.
What does that permanent gap, that difference between the ultimate perfect mathematical truth and the physical reality we actually observe and interact with, what might that imply? Does it say something about the limits of our own knowledge? Or maybe something about the nature of divine intention, if you accept that premise? Or the relationship between the ideal and the real?
Definitely something to think about. A potential connection between ultimate truth and our observed reality, worth exploring further on your own.